Okay, so the different things we'll be looking at, this first one is the one we'll see probably more often than any of the others. The effective concentrations, if it's molarities, or it could be partial pressures, if it's a reaction that's about gases. If you increase the concentration of a reactant, it's going to drive the reaction to the right. So we've got this imaginary reaction again, A plus B yields C. It was at equilibrium, everything was looking good, and then somebody came by and they added more reactant. So I put a little up arrow next to it to show reactant has been added. If you add more reactant, that is going to give you more reactants. That messes up your equilibrium constant ratio. So to counteract that effect, the reaction is going to push itself to the right, make more products until it gets back to that equilibrium constant ratio that it was supposed to be at in the first place. So when I put an up or a down arrow, like that black arrow next to a particular reactant, if it's up, it means I'm increasing its concentration. If it's down, it's decreasing it. The shift will always go away from an up arrow. It'll go away from an increase. So if you had another reaction that was already at equilibrium, and you increase the concentration of a product over on the right-hand side, put an up arrow over here, that's going to push the reaction backwards so it can get back to that equilibrium constant ratio. So it was at equilibrium, then you messed up the ratio by adding too much product. So to get back to it, the reaction is going to shift to the left and make more reactants as it uses up that product that was added. Both of these changes where you change the concentration, or if it was gases, you would change the partial pressure, these don't actually change the equilibrium constant value. It's just the reactants and products will shift so they get back to that steady value for capital K, the equilibrium constant. Okay, so if you increase something, the reaction is going to shift away from the increase. If the increase is on the left, the reaction pushes to the right. If the increase is on the right, the reaction kind of goes backwards, and we say back to the left, or toward more reactants. Raise your hand if you need more time here. All right, great. All right, the other thing you could change, instead of increasing something, you could decrease something. If you decrease something, it kind of pulls the reaction towards the decrease. So decreasing the concentration of a reactant over on the left-hand side. I'll put a down arrow to show maybe the reaction was taking place in a container and I started pumping some of one of the reactants out of the container. So I decreased its concentration. That is going to pull the reaction backwards toward the decrease, again, to make up for the change. That's what Chateliers Principle is about. In doing so, it uses up more of C and makes more of each reactant, A and B. Even though we only messed with reactant A, it could actually end up making more of B by pulling the reaction backwards. And then the last sentence is how a lot of reactions might be driven forward. Decreasing the concentration of a product drives the reaction forward or to the right. So as the reaction proceeds, if you can pump some of the product out of the system, that's really good because that can help drive that reaction forward. So the reaction will be driven towards any decreases. And that last one is especially useful if you're like trying to make a product. Like if we go back and think about when we made aspirin, that reaction isn't very efficient. Even when we tried, our percent yields were still like 40, maybe 50% if you got lucky. One of the things we did to try to drive that one forward in the first place was, do you remember when you made your precipitate and you put it in the ice bath? So the reaction happened on the hot plate, and then you had to put it in the ice bath for a little while. Remember doing that? That decreasing the temperature was supposed to help make more precipitate. And when the precipitate forms, it kind of comes out of the solution. So in that way, we're not pumping it out of the container, but by making it a solid precipitate, it's coming out of the solution. So by decreasing the temperature on that, we were trying to pull the product out of the equilibrium mixture to try to make more and more aspirin form. And so that's one of the things that in general that a chemical engineer might do for a job is how to set up a reaction chamber, maybe on a huge scale like the size of this room or something if they're going to try to sell it, in a way that pumps the product out in some way or another so that the reaction can continue making more and more product. Even if the reaction itself isn't very efficient, you can manipulate the chamber to pump product out, and that'll drive the reaction forward, so you try to use up all your reactants and be as efficient as possible. All right, so those last two, those are the changes we're going to see most often, are changes in a reactant or product. The other couple of changes we're going to look at involve temperature change and the volume of the container. Now, one thing about temperature change that's different from changing a concentration, the temperature changes actually affect the value of K. But the idea we can think about it is going to be the same thing. If it's an exothermic reaction, just write the word heat as if it's a product. And then you can still use that arrow method that we were using just before. For exothermic reactions, adding heat, okay, that would be increasing the temperature. Is almost like increasing the concentration of a product. So increasing the temperature drives that reaction back toward more reactants to the left. It's really because it changes the value of capital K, the equilibrium constant. But if you just have to predict whether it's more reactants or products, you can just put an up arrow next to your product heat because it's exothermic. And remember that the reaction always goes away from any increases. And that way it would use up some of that heat that was added as it goes backwards and makes the reactants. And a lot of the problems aren't going to say the word exothermic in front of it. They're going to say delta H is negative, or they'll say delta H is less than 0. That's how they like to show it a lot. Raise your hand if you need more time here. All right. How about now? Anybody need more time? Okay. If you have an endothermic reaction, just like we did on that bell ringer before, just put the word heat down as a reactant because endothermic reactions need to absorb heat and take it in, kind of like it's a reactant in the reaction. Again, it's really not matter, it's just the energy. But if we can think of it more concretely like that, then if you increase the temperature, it was at equilibrium already, then you went and changed things, you increased the temperature. That's going to push the reaction forward. What that actually does is it increases the value of the equilibrium constant. And then to make up for that, more reactants have to produce more products, and you end up getting more products in the end. But you can always just think of it as the reaction is going to shift away from any increase as it tries to restore and get back to equilibrium. Raise your hand if you need more time here. Good. And again, a lot of the problems are just going to say delta H is greater than 0. That's going to be their code for telling you, hey, this is endothermic. Anybody need more time now? All right. All right, volume is one that you focus on gases. This kind of takes us back to something we did with entropy before. We were like counting the number of moles of gases on each side of the reaction. That's going to be how we think about the changes in volume of the container. So reactions that involve gases can be shifted one way or another based on increasing or decreasing the volume of the container. So the important stuff I kind of put in the box here, things to think about. Decreasing the volume or having a smaller volume drives the reaction toward whichever side has fewer moles of gases. Larger volume drives the reaction toward whichever side, whether it's reactants or products, left or right, has more moles of gases. So the reason this happens is because both molarity or partial pressure are related to volume in some way. So if you change the volume, you actually are changing the concentrations of your gases. An easy way to remember it and think of it is just fewer moles of gases fit better in small volumes and more moles of gases fit better in large volumes. So it's an easy way to just make your prediction. But again, it's really because when you change the volume, you're changing the concentrations, and the side that has more or less number of moles of gases is affected differently by that change in volume. So in this way, it's still like the first things we talked about, changing concentration or pressure, how the reaction wants to get back to that original equilibrium constant ratio. But it's really easy to make these predictions because you just count on each side of a reaction your number of moles of gases. If it's the same number of moles of gases on each side, then it wouldn't really have much of an effect. But let's go back to our imaginary reaction and we'll put some coefficients in front of it. So if it said like 2A gas plus B gas yields something like 5C gas. Then I'm going to count up. The left side of this reaction has a total of, just add up the coefficients, 3 moles of gas. And the right-hand side has 5 moles of gas. So just base it on the coefficients on each side. My right-hand side has 5 moles of gas. So if this were my reaction and they said, what's the effect of increasing the volume of the container? Increasing the volume would drive this reaction forward toward making more products because the right-hand side has more moles of gas. It's favored in larger containers. If they said, what's the effect of decreasing the volume of the container? I would have to say that drives the reaction backwards toward more reactants, A and B. I can just think of it because fewer moles of gases fit better in that small container. But again, it's really because you're changing those partial pressures when you do that. Does anybody need more time on this slide? All right. So let's practice using Chateliers Principle a little bit. This one, you can can just, don't worry about copying this down in this. Just try this one along with me, because again, on the quizzes, thing that you'll do in a minute, you'll get to do your own practice individually, but I just want you to help out with this one, so I don't think you need to copy it down. In which direction will the equilibrium shift when N2O4 is added? So let's look at our reaction and find the N2O4, and I'm going to put an up arrow beside of it, because it's over there. I'm going to put just an up arrow right here. So if you increase that, you put an up arrow next to it on your reaction, or just imagine it there. And as far as which direction, we can just say left or right. Sometimes it'll say toward more products if it means right, toward more reactants if it's left. But MK, do you think this will shift the reaction to the left or to the right? To the right. Right is right. It's going to be to the right. Anytime you have an up arrow, the reaction is going to be shifted away from that up arrow. In order to restore it back to equilibrium, it needs to use up some of that extra N2O4. So for A, I'll just say to the right. And I'll start over again for part B. NO2 is removed. All right, so in terms of this arrow method, here, Pavitra, should I put an up or a down arrow beside of NO2 for part B? Down arrow, yeah, because I'm removing it. All right, so if I remove it, people aren't here. Kira, which way would that drive the reaction if I remove some product? Good job, to the right. It's going to go toward any decreases. So B is right again. All right, now let's look at letter C. The total pressure is increased by the addition of N2. Ainsley, is N2 gas? Is it in this reaction? N2 gas? Huh? Yeah. So letter C says the total pressure is increased by the addition of N2 gas. Do you see N2 gas in this reaction? Right, it's NO2, isn't it? N2 itself isn't in this reaction. So this is a trick question. If N2 isn't in this reaction, it's no effect. Sometimes people like to overthink that, and they're like, okay, you increase that, does that change the pressure, does that change the volume? Nope, it just says they added some extra gas that's not even involved here. And so that, you can think of it as a trick question to try to make you overthink something or something like that. But in this one, it's not a reactant, it's not a product. It's nitrogen is what we call an inert gas. It's not going to react with anything in this at all. So if it's not in the reaction, don't overthink it, and the answer is just going to be no effect. The volume is increased. What are we supposed to do when the question is about changing the volume? Davis, what are we supposed to do? How do we approach it when it's about a change in volume of the container?
You count the number of moles of each gas on each side.
Nice. Count the moles of gas. How many total moles are on the left side, Adam? 1 mole of gas on this side. How many total moles are on the right side, Jonathan? 2. Just use those coefficients. If there's an aqueous or a solid, don't count it. We're only going to count the gases because they're the ones that can be affected by these volume changes. Okay, so the volume is increased. If the volume is increased, which way do you think this would go, Will Parker? Go to the right. Good, the side with more gases. Right, or the answer might be more products or toward making more NO2. All right, last one here. This is where we get back into that idea of endo and exothermic. The temperature is decreased. First of all, Maddie, is this an endothermic or exothermic reaction? Very good. That's a positive number there, so it's endothermic. If it's endothermic, should I think of heat as a reactant or should I think of heat as a product for endothermic, Piper? Yeah, good job. So I'm actually going to physically write the word heat over here. And that's what you can do anytime you are dealing with a temperature change question on one of these Chateliers Principle. So if the temperature is increased, would that mean I have more heat or less heat? Sorry, the question says decreased. If the temperature is decreased, Joseph, do I have more heat or less heat if the temperature is decreased? Less heat. So I'm going to put a little down arrow next to the word heat. And then just remember, just like with concentrations, the reaction always is driven toward the side with a down arrow, toward any decrease. So Shelby, what's my final answer here for the direction, left or right? Good job. It is to the left. All right, so all those questions were about what we've talked about with Le Chatelier's principle so far. There's one more thing that some of these questions will ask about, and that is about a catalyst. What would happen if you added a catalyst to the reaction? It would explode. Should it go to the right if you had a catalyst? Should it go to the left if you had a catalyst?
Both.
What's that?
Both.
You are correct. So we call it the non-effective catalyst. It drives it to the right and the left equally, so that it ends up not having an effect at all. It makes the reaction happen faster forward, so it does get to equilibrium faster, but a catalyst also lowers that activation energy for the backward reaction too. So Adam is exactly right. It is both. And so I call it the non-effective catalyst. So just like on that last one, there was that one question where the answer was no effect, where they had to throw us a curveball and make us overthink it. Sometimes they'll have a question that is about catalyst. So with a catalyst, equilibrium is achieved faster because it does speed up the reaction, but the equilibrium concentration remains unaltered. So therefore, it does not shift the reaction either way because it's helping out the forward reaction and the backward reaction get there faster, but it helps both sides. So watch out for questions about reactant, or watch out for something about a substance that's not a reactant or a product. They just threw something extra in there. And then also watch out if they mention a catalyst. No effect. So that diagram is something we saw back with kinetics. It's showing the activation energy is lowered, the hill is lowered. We usually think about reactions just taking place forward, so we think the activation energy is lowered for the forward reaction with A becomes B. But with equilibrium, remember, we're also thinking about a reverse reaction where B goes backwards and becomes A. And in that way, that catalyst has also helped out the reverse reaction. So both sides were helped out. So we still get to the same equilibrium mixture. All right. So what I want you to do first is you can just go to, I think, quizzes.com, and you can put the code in that's shown there, the 177 number. And there's, I think, about 10 questions, kind of like the practice question we just did in the notes, where it's going to give you a reaction and it's going to have you predict a shift if you add this or that or the other. So if you go through it and you make it 90 or 100%, this one itself isn't for a grade, but I thought this would be, like, it's not going to go in the grade book. But I thought this would be good, so you could say, okay, I know this stuff pretty well, or if you go through it and you make a 40 or a 50%, then you might want to go through it again and have me come over and explain something to you or talk about it with you.
So you don't need to turn it in at all?
Correct. This one you don't need to turn in. I haven't even posted it as an assignment in Canvas, but I just have the link and then the join code right up there. When you finish it, then you'll want to work on the